and a very good morning to Encik Zaki and our fellow friends. So today, I Kaviindass anak lelaki Nageswaran, my matrix number 01DAD20F1007, and some friends gonna present the case study of the course which is DJA50082 vehicle dynamics. So we take the car Mitsubishi Galant on the year 2004 for our case study. So there will be this is the agenda of our case study, and we got introduction, specification and assumption, calculations of dynamic loads, tire changes and effects, traction limit and traction force, braking hypothesis, aerodynamic and drag reduction modification, comfort, natural damping frequency, conclusion, and last but not least, we also got reference. So this is our team. First of all, we have Jaiguhan A, Sivakumar, which is matrix number is 01DAD20F1009, and we got also Sarvess A, Ganesan, which is his matrix number is 01DAD20F1015, and last it's me, Kaviindass A, Nageswaran. My matrix number is 01DAD20F1007. So let's go to our intro. Okay, the 2004 Mitsubishi Galant is available with the choice of two powerful engines, which is the DE and ES trimlines, which is equipped with a 2.4 liter 4-cylinder engine and mated with a 4-speed automatic transmission. This engine delivers 160 horsepower and 157 pound-feet of torque with the aid of its patented Mitsubishi innovative variable timing and leaf electronic control, which is well known as MyVac system. For even more performance, the LS and GTS trim lines include a high displacement and a high output for the 3.8 liter single overhead cam V6 engine mated to a 4-speed Sportronic TM transmission that allows the driver to select shift points. The new V6 develops to 230 horsepower and 250 pound-feet of torque, which is the highest torque rating in the class. In this case study, we will focusing on complete aspects of the Mitsubishi Galant based on the requirements around the study and focus on parts of dynamic loads, tire changes, and its effect on the drivability, performance, comfort, and other areas. This case study also aims to further understand and relate to the course DJA50082 vehicle dynamics, which taught by our amazing lecturer, which was Mr. Zaki. It is our aim to study aerodynamic effects on fuel consumption, drags, and ways to improve the Mitsubishi Galant in order to improve our drawbacks. Okay, after this, it will be continued with some of the topics with my friends. Thank you.
Thank you, Kaviindass. From now, I will take over the presentation. Which is, my name is Jaiguhan, son of Sivakumar, and my registration number is 01DAD20F1009. And I'm going to present about the specification and assumption of the car. So, as we all know, The car that we choose for this case study is a Mitsubishi Galant 3.8 liter GTS. Is a model which is came out on 2004. This car is really suitable for our daily use and also suitable for vacation. Example, like if we want to go for holidays, we can use this car because it have a good engine type, and also it has a really big space which has 5 seat and 4 doors. It may we can occupy a family in this car. Other than that, this car start of production was 2004 and the end of the production was 2008. The body type of this car is a sedan. It means it's a long car like the picture I've shown here. Other than that, the specification of this car, we have engine spec, which is the power is 230 horsepower and the torque is 250 newton per meter. So, and also the diameter, the car is quite a long car, which have a 4865 millimeter and a height of 1485, and the tire size is 250 per 60 and the radius is 16. The which meanwhile the wheel rim size is 6.5 J times 16. These are the specification and the dimension of the car. This is the roughly sketch of the car just now to show where is the height and the weight of the car. So this is the wheelbase of the car, which is the unit is in inch, and also this is the front front wheel weight of the car, and this is the rear weight of the car, and over here is the center gravity of the car. So this is just a roughly sketch for the car. So from now Sarvess will take over. Thank you.
Greetings and good day. Thank you to Jai and Kaviindass for the introduction. I'm Sarvess Ganesan, registration number 01DAD20F1015. I will be discussing about calculations of dynamic load. As you can see here, the car that we have chosen is a Mitsubishi Galant from the year 2004. Based on our research and our study, we have found out that the total weight of the car is 4541 pounds, which is also 2059.76 kilograms. Weight at the front and weight at the rear is stated at 1129 and 90 kilograms and 929.86 kilograms. The wheelbase of the car is 2.75 meters. How we can calculate the distance of B and C with the given information is by this. WFS equals W times C over L. Hence, we know that at the front, weight at the front is 1129.90 kilogram equals to weight in total 2059.76 times C divided by wheelbase 2.75. And after our calculation, we can see that C equals 1.508 meters and B becomes 1.242 meters. Moving on to the next question, where we are going to be calculating the dynamic load of the car. We have data which is weight in total 2059.76 kg, weight at front, weight at rear, the acceleration of the car at 12 meters per second square, wheelbase 2.75 meters, B and C we have calculated just now, which is 1.242 meters and 1.508 meters. Grade at 9%. So how we calculate the angle of the grade is by using tangent theta equals 9 over 100. 9 over 100 because a percent, 9% is 9 over 100. So tangent theta is 0.09. Tangent at the end, tangent theta, and theta you get 5.143 degrees. Weight distribution, we get after calculating, we can understand that weight at the front and weight at the rear, it comes to about 55% at the front and 45% at the rear. Accurately, we get 54.85591%, but we are assuming we're rounding it off to 55% to make it easier for our calculation. Same thing with the 45%. We get 45.14410, but we are simplifying it to 45% at rear. Now, here are some assumptions that we have to clear out is that one, weight distribution. As I've said, we fix it to 55% at the front and 45% at the rear. H, height of the center of gravity. After searching out, we came down to a final value which is 0.48 meters. Now calculating in a everyday scenario, a real life scenario where the weight of the car is being driven by the driver with his family. So let's say a weight of the driver is 90 kilos, assuming the weight of the family of three with two children and maybe the spouse. So it's 50 kg plus 60 plus 80 kilograms, which is 190 kilogram. Total weight of the passengers would become 280 kilograms. So four of them. How we are going to distribute this now is that passenger 280 kilograms, 55% at the front, 45% at the back. So 55 over 100 times 283, we get 154 kg. At the rear, we get 126 kilogram. So now, as at this calculation, you can see WF plus WFP, weight at front and weight at front of passenger. So weight at front 1129.9 plus 154 is 1283.9 kilograms. Weight at rear plus WRP equals 929.86 plus 126 equals 1055.86 kilogram. So sum of total moment B, clockwise positive, we can see WRL plus DAHA plus WDAXH plus HH plus RHZ, DH plus L plus WH sine theta plus WB cos theta. DAHA, aerodynamic drags, we are neglecting. We are not calculating it. We are not taking it into consideration. So at the end, the formula comes down to WR equals W cos theta B plus W over G AXH plus W sine theta H over L. So after adding in all our values, towards the end, as you can see, our value sum of moment for B, clockwise positive, is 13718.20 Newton, which is 1398.40 kilograms.
Thank you, Sarvess. Without any delaying, let's proceed to our title, which is tire exchange and its effects. So, the tire is the main component of a vehicle. Without tire, we can't move the vehicle. So, in that case, tire is also an important part of the vehicle. So, what will happen if we change our tire size? There are advantages and disadvantages of changing tire size. One of the advantages of changing the tire size into a bigger scale, it will improve the stability of the car and also the range of braking distance will be shortened. And the disadvantage is a larger diameter means that the wheel will be heavier and consequently the speed will be slightly compromised during acceleration. The third one is comfort will be compromised because tire will be harder and suspension risk faster corrosion since the rim have a major impact on the surface on the road. And the third disadvantage is bigger wheels will also affect fuel consumption since driving will be a little bit slower car mileage will increase but depends on the power of the vehicle. So what will happen if we change into a smaller tire? Because smaller tire allows us for a fighter turns, which means a sharp corner turns like that. But it's all depend on the type of vehicle and the tire are mounted on. Other than that, bigger wheel also increase the maximum load of the car. There are a lot of new cars that offer multiple wheel size, but which are the best one? Bigger wheels look cool, but wheel and tire size has huge effect on riding. So a study of case study have been through a type of review where they are a Volkswagen Golf GTI to make a test track in a south of France and compare how it drives on the fair compressor, which is the size of 17 to 19 inches. Wheel that available with from the factory to make it fair comparison, so we can compare which size tire is better. Tire we use is a Goodyear Eagle F1 tire brand. 3 tire in performance test, which is the 17, 18 and the 19 inches of tire. So we have 3 sizes of the tires. So the tire are test in 2 type of surface, which is in dry and also wet. They will be handling braking test plus accumulating the test in a 3 package of performance nearly indicatedly perform. The biggest difference between the 3 wheel size were subjective. Noticeable different ride and handling characteristic if you swap size, even if the unlimited performance test data doesn't show major difference. That's all for tire and effects. Let's go for the transaction limit and transaction force. The traction limited for this car. To calculate the traction limit force, we need several information, which is the main thing is coefficient of friction, which is the value is 0.6, and we need mass, which is the weight of the front wheel, which is we have to convert the weight into we have to convert the mass into weight, which means we have to change the kilogram to newton, which is the value is 20,110.5, and the length is, which is the wheelbase is 2750 millimeter. We have to change it into millimeter, which is 2.75, and this is the rear wheel load, and this is the second one is the H is center gravity of the car. So over here is the formula to get the tractional limit force, the locking system. So we have, first of all, we have to times the coefficient friction with the weight. After that, we have to divide it with the formula given, which is 1 minus 1.24, which is 1.24 is the center gravity of the car and also the wheelbase. We have to divide with it and also time with the coefficient friction. So we will get 0.3. After that, we will get the main answer is 9117.5. So from that we can know that during acceleration, the force from the engine creates a momentum that the tire rotate the vehicle around the driven wheel. For a real driver car, this is a beneficial by increasing vehicle force and increase the tractional and the wheel force. For a front wheel driver, car tractional force will be reduced during acceleration. Let's go for the fractional force. So, fractional force, we have to calculate the force involved for all the gear. So, we have 4 gear over here. So, the first gear ratio is 2.84, and the second one is 1.57, third one is 1, and the fourth one is 0.69. And we need 3 more information to complete this formula, which is final drive ratio, which is 4.21, and the torque max power, which is 250, and also the radius of the rim, which is 0.203. So here we have the formula, which is force equal to the power of torque, and we have to the NTF is the multiplication times of the gear ratio times with the final drive ratio, and we have to divide with the radius of the rim. So here we have the formula for the first until the fourth gear. So this is how to do the tractional force. For we have the answer for the all the gear, which is the first gear is 14724.63 Newton, and for the second gear is 8140, and the third gear is 5184, and the last gear is 3577.46 Newton. So these are the tractional force that are needed to be solved. So let's see about braking hypothesis. So for brake, when brake force increase, torque also will increase. Like example, brake force is directly proportional to the torque. So brake force inversely proportional to the radius torque. So the hypothesis that we can do from here is, when a brake force increase, the total braking torque and rotation inertia will increase. Brake force is directly proportional to the total torque and rotational inertia. Drag component. Drag coefficient component for body of the vehicle, which is have 4 type, which is underbody, forebody, skin body, and after body. So let's see what does the drag component effective in a car. For an example, drag component, which is a forebody, is the most significant drag reduction can be achieved by rounding up the vehicle and upper horizontal leading edges on the front face, because the drag reduction of the front spoiler is large if its use is combined with rounder leading edges. So these are the forebody function. Other than that, we also have underbody. What is underbody? Underbody is a suspension, exhaust system, and other suspension, exhaust system, and the other pro-turning component of the underbody responsibly for the drag. Smooth underbody panel help to minimize the underbody drag, which will help the car to go more faster and also smooth. That's it from me. From now, my teammate will take care of it. Thank you.
Greetings and good day. Thank you to Jai and Kaviindass. I'm Sarvess Ganesan, registration number F01D8020F1015. I will be discussing and touching about aerodynamics and drag reduction. Aerodynamics or vehicle aerodynamics is a science of how air flows around and inside objects. More generally, it can be labeled as fluid dynamics because air is really just a very thin type of fluid. Above slow speeds, the airflow around and through a vehicle begins to have a more pronounced effect on the acceleration, top speed, fuel efficiency, and handling. Therefore, to build, alter, and create a better version of the Mitsubishi Galant that we have decided to do the case study on, we need to understand and optimize how the air flows around and through the body, its opening, and its aerodynamic devices. So let's go into the theory of aerodynamic principles. We start with drag in vehicle aerodynamics is comprised primarily of three forces. One being frontal pressure or the effect created by a vehicle body pushing air out of the way. Two, rear vacuum or the effect created by air not being able to fill the hole left by the vehicle body. Three is the boundary layer or the effect of friction created by slow moving air at the surface of the vehicle body. Frontal pressure. Frontal pressure is caused by the air attempting to flow around the front of the vehicle. As millions of air molecules approach the front of the car, they begin to compress, and in doing so, raise the air pressure in front of the car. At the same time, the air molecules traveling along the sides of the car are at atmospheric pressure. At the front of the car has a lower pressure compared to the molecules. That is what frontal pressure means. As you can see, here are indications, legends to where flow velocity and density is indicated, air pressure, green, yellow, and red. So green indicates low pressure, low velocity, low density, and R increases red increases high. Here we can see the car by frontal pressure, the car is moving straight. So vehicle is moving straight and opposing it is air. So as the air molecules collides with the car body, it the pressure increases. So from low density, as it comes towards the vehicle, it becomes higher. That is what meant by frontal pressure. And when a rear vacuum here again same identification where green is low and red is high. As you can see here, rear vacuum is meant by air that cannot fill vacuum behind window and trunk. So at this area, it is vacuum. Air air is not present there. So that is what is meant by rear vacuum. Now let's go into how we can improve aerodynamics. And to do that, we must understand uh, factors that affect affect how the car cuts the air, or how efficient it is, or how aerodynamic it is. One important factor that stops or impacts aerodynamics is turbulence. Turbulence is created by the detachment of an airflow from the vehicle. The final unavoidable detachment of the very rear of the vehicle leaves a turbulent wake. So when the flow detaches, the airflow becomes very turbulent and chaotic when compared to the smooth flow on the front of an object. Let me give you an example from airplanes. I'm pretty sure many of us have been on airplanes, and sometimes when we are in the air, the the captain would always ask us to sit down and remain seated with our seatbelts when the plane starts shaking. And what we understand in most cases is this is called turbulence, where at some parts in the atmosphere, the air or the wind isn't the same all around. So when at a different points where it hits the wings or hits the body of the plane, it causes turbulence where the airflow isn't very smooth. So when it's not smooth, it affects the plane's stability. Now add that into bring that back into cars. Maybe we don't feel turbulence as bad as planes, but if we are really studying to how we can improve the vehicles aerodynamics, improve the cars' fuel economy, Turbulence is a major factor that we must find ways to overcome if that is our focus. Another point is drag coefficient. To enable the comparison of the drag produced by one vehicle versus another, a dimensionless value called the coefficient of drag or CD was created. Every vehicle has a CD which can be measured using wind tunnel data. The CD can be used in drag equations to determine the drag force at various speeds. CDs for the Mitsubishi Galant that we have studied after going through multiple Google Scholar research papers was that the CD have finally come down to 0.35. So that is an average value between sedans. Here, here is the front bumper. Front bumper of the vehicle. This is the standard factory bumper, and this is altered. Okay, to do that is to add a air front dam. How it works is by adding a front dam. It works as a front dam. Let me explain. One way to reduce drag is to minimize the frontal area. The smaller the hole your car punches through the air, the better it will accelerate. The higher top speed and the lower fuel consumption it will have. It is usually much easier to reduce the frontal area than coefficient of drag. Second point is to add front air dam. Many car owners add a front dam for aesthetics, but a front dam serves another purpose, which is to redirect air and to improve the vehicle's aerodynamics. More specifically, a front air dam increases downforce and decreases drag by decreasing the amount of air flowing underneath the car. Air dams at the front of the car restricts the flow of air from reaching the underside of the car. This creates a lower pressure area under the car, effectively providing downforce. In many cases, air dams also reduce the coefficient of drag of the vehicles. So looking at this image, this is the front bumper of a Mitsubishi Galant that has been studied and altered. You can see that the shape from more of a box becomes streamlined. So when streamlined, instead of air just directly hitting and going to the side, air now has a channel to go through. It has a way to be pushed out. And with air dams at the bottom, or it's usually called the lip kit, a bumper lip kit, how it's very close to the ground, so not much air actually goes below the car, and with that more air gets pushed to the side or to the top. So that is what air dams mean and how they impact the car's aerodynamic. Okay, when now we are also talking about scoop or positive pressure intake. We have seen multiple cars that has scoops, roof scoops or bonnet scoops. A lot of Subarus you have seen, a lot of Subaru STIs, even some upgraded Mitsubishis have. How it works is that, again, green means low density, red means high. So the air, let's just assume this is a scoop. So air goes in low density, medium density, high density. So that air that is being channeled out just now has a direction to go into the engine intake, where the air is not wasted. We are also using the air to increase the efficiency of our vehicle. So how it works is that the air compresses in expanding volume airbox as it slows before entering the engine. Another way to reduce or increase aerodynamics is by using NACA ducts, NACA ducts, named after the National Advisory Committee for Aeronautics. NACA ducts are useful when air needs to be drawn into an area which isn't exposed to the direct oncoming airflow the scoop has access to. So after studying about the scoop, we are coming down to NACA ducts, which are all related. In a way, it affects each other. Quite often, NACA ducts will be used along the sides of a vehicle. The NACA ducts takes advantage of the boundary layer, as I've explained just now, the boundary layer, a layer of slow-moving air that clings to the bodywork of the car, especially where the bodywork flattens or does not accelerate or decelerate the airflow. Areas like the roof and the side body panels are good examples. The longer the roof or the body panels, the thicker the layer becomes, a source of drag that grows as the layer thickens as well. This Naka duct scavenges the slow moving area by by means of a specially shaped intake. The intake shape shown below in the diagram drops in towards the inside of the bodywork, and this draws the slowly moving air into the opening of the end of the Naka duct. Vortices are also generated by the walls of the duct shape, aiding in scavenging. The shape and depth change of the duct are critical for proper orientation, operation. Typically, uses for Naka ducts include engine air intakes and cooling. Uh, this is a Naka duct. Naka, remember, is shape named after National Advisory Committee for Aeronautics. As you can see, air flows towards the rear of the vehicle. What a Naka duct does is that it takes advantage of the boundary layer, a layer of slow moving air that clings to the bodywork. So by using Naka ducts, we are heavily improving the aerodynamics, and we are reducing drag of the vehicle, hence over hence which improves the performance of the car, which improves fuel economy because we have substantially reduced drag, so we are not cutting air as heavy, and because of that fuel economy improves. We have better performance, sometimes we have better handling, we have better downforce. And since the Mitsubishi Galant is also used for a family car, fuel economy and fuel consumption will be a big concern for consumers. And by using all the stated suggestions and descriptions that we have descriptions and designs we have done to the Mitsubishi Galant, it it is substantially proven that all these factors increase aerodynamic and reduce drag.
So I'm here again to explain my part, which is comfort and natural damping frequency. The tire stiffness. Before start our calculations for the question 4, we gonna search for some information, which is like tire stiffness, suspension stiffness, front damper, wheelbase, CB, mass of the wheel, weight of the car, and with these numbers we gonna find for natural frequency for the front and rear wheel, and natural damping for front and rear wheel, and last but not least uh, WD for the front and rear wheel. So this is the whole calculation for the uh, rear and front wheel, and we got WD for the rear front wheel, which was 0.57 Newton s meter, and for the rear wheel we got 0.54 Newton s meter. Okay, so there are some explanation for the calculation before this, which is the natural frequency of the suspension elements within frequency range 50 to 200 Hz. It should not be below from the 50 and above from the 200, so that the suspensions, if the range of the natural frequency is low or high than this range, it is in a bad condition. So next, by choosing a specific frequency for the application which is still a little beyond in our current knowledge base, however, we should choose the calculation. This is the guideline for the calculation of the uh, FN. Okay, if the range between 0.5 to 1.0 Hz, it is a passenger car, or typically it's a OEM. And from 1.0 to 1.5 Hz, it's a typical lowering springs. 1.5 to 2.0 Hz rally cars is rally cars. 1.5 to 2.5 Hz is a non-aero race cars or moderate to downforce formula cars. 2.5 to 3.5 Hz is moderately downforce race cars with up to 50% total weight in max downforce capability. And lastly, 3.5 to 5.0 or more than it, it is a high downforce race cars with more than 50% of their weight in max downforce. And as stated in question 4, does the tire size will affect comfort of ride? As a general rule, bigger wheels result a rougher ride. Switching to a smaller wheel and a thicker tire can give you a smoother ride without any major modification to your car. One of the most important components related to vehicle dynamics is the tire and the wheel set. According to their dimension, the wheel dynamic behavior and driving comfort are seriously affected. So it is said that vehicle dynamic behavior and driving comfort are seriously affected by the tire sizes, and the bigger wheels will result a good ride. Okay, that's all from me. Thank you.
Thank you, guys. So, here we are at the end of our case study. In conclusion, the case study was on the one of the best way to learn about the real life vehicle. We have learned a lot by doing this case study, which means we have create lot of calculation. We have done a lot of calculation which help us to know which is the better design, which how to calculate the weight, the suspension, the stiffness. We have learned what will happen if we change the tires by calculation. So we have learned a lot about a real life car by doing this case study. Other than that, we also have faced several problems by doing this case study. One of the problem is that we have faced is picking a vehicle that is suitable for our case study, because we need a vehicle which can be used for our daily life, example like going for groceries, going for our workplace, and also going for the vacation. So we have to find a good car that are suitable for all these particular situation. So at last, our group have come picking up Mitsubishi Galant because it have all the characteristic to be studied for this case study. We also divided the task equally so that we all, each and everyone, can gain a lot of new ideas and also can bring this case study to another level. We Google about this car to get some data which help us to complete the case study. By doing this case study, we gain a lot of knowledge about this car and also this subject. These are the reference that really helped us to complete our case study, which is the first reference was about the car. So this is where the link that we have gained the data for the car, and also the second reference also lead us to the data of the car and also helped us to complete the case study with a good information for us. That's all from our team. Thank you.